The second part of the talk concerns basic knowledge on beach morphodynamics. Well, so you can see on this graph the organization of the nearshore zone on the beach. And for example, we already discussed about this part, which is offshore zone, with where the waves can coming to the shore with no major changes, and this part, which is the active zone. Here is the shoreline. So you can recognize that on the shoreline there is some bars, and we're going to speak about that right now. The swash zone here it is, the bear, and after the fordune and the dunes. You just first keep in mind that the morphology of the beach change during winter and summer. I mean during storm condition and summer condition. In this figure, it is a profile along the Italian coast, and you see that the orange part represent the summer profile. And in the winter, you see that the beach is eroded because of the waves actions, and the sun from this part is moving in the offshore direction. You see that the sun is accumulated during the winter condition on the bar. And during the summer, the sun is coming back, is moving onshore, close to the shoreline, and like this, the beach is bigger. Well, so we can describe this general behavior, but in details, few examples on what's happening during storm condition. Because it is a simple example, but on the field, it used to be very different. We may have a look on this part. You'll see that there is a profile with a dune, a berm. This is a beach face, the inner bar, and the outer bar. In that case, we are in what we are calling longshore bar through systems. I'm going to speak about that later. You can consider that this morphology is representative along the shore. So after a storm, you'll see that there is a retreat on the shoreline position with the sediment deposit here. And the inner bar is a little bit moving offshore like this one. On this condition, it is more or less the same behavior, but it is strongest because the waves was strongest. And the evolution of profile is very connected to the wave energy and the sea level, not exactly, I should say, the water level during the storm. You see that there is a large retreat of the beach face, and consequently the shoreline retreat. The inner bar is slowly moving offshore, and the outer bar is clearly moving offshore. And you can also compare in this part that the shoreline, or sorry, the profile do not move a lot. There is not a lot of change. I explain this concept in this graph. You see this one concerning the little change here, you said there is no change. It is because we are calling this point here, the limit between no changes and large changes is what we're calling depth of closure. In the lecture, we have some, I give you some indication on what depth of closure here. So you see that there is a retreat on the berm, on the beach face as well as on the other case, and there is a offshore displacement of the outer bar. This one seems to be quite stable, but actually it is probably related to the field measurement because it's difficult to come back very quick after a storm. So probably the inner bar is the bar which is moving all the time because the waves action are always present. So you should keep in mind that sometimes we have some field measurements, but we have to interpret the field measurement regarding to the methodology and the time you do the measurement. Another example, you see that there is a very few change on the beach face on this area. Meanwhile, the bars are moving offshore, and it's a little bit different. And than the other situations, and sometimes we have difficulties to find and to define wave energy which simulate shoreline retreat and bar movement. It's a very challenging, actually. If you are very, let's say, if you are going on the beach very often, probably you observe that some beaches are similar and others are different. Well, so few, well, not few, but more, half a century ago, two researchers from Australia observed this morphology and proposed a conceptual model that is called the morphodynamic state. The idea is that there is several states which can be organized, and I show you these states. The first one is when the morphology of the beach is what we're calling dissipative state. In that case, beaches are exposed to energetic waves, often with relatively long periods. Waves start to break here. They start to break far from to the shoreline, very far away from the shoreline, and the surf zone is very wide. Here you see that the surf zone is a very wide, several thousand, not thousand, sorry, several, a lot of, between 100 and sometimes 500 meters. Waves break gradually across this wide area, usually as spinning breakwaters. This is the wave morphology. As a result, most of the wave energy is dissipated before reaching the swell zone. This is why we're calling this morphology dissipative beaches, because of the dissipation of the waves in this area. The currents are generally diffuse within the surf zone, and electron currents may be present, but recurrent are usually weak and poorly organized because of the waves energy. The waves energy is spread over a large area. So keep in mind that the morphology is when you have a very flat beach with a finer sand. On the opposite, sorry, this is a picture, and have a look what a dissipative beach is looking. In this part, you see that the surf zone is very important. So there is a large dissipation of the wave energy. On the opposite, the reflective beaches show a very important slope. These beaches, the dissipative, are usually exposed to lower wave energy or waves that break close to the shoreline. The breaking point is very close to the shoreline. And wave breaking occurs mainly in the swash zone, often as a plunging breakwater, but sometimes, well, and surging as well. This process of strong reflection of wave energy back to the sea. This is why we are calling this state reflective state, because there is a lot of reflection. And the currents are mainly controlled by the swash motion. Water runs quickly up to the beach and then flow back down during the backwash. And rip currents are generally weak or absent because the surf zone is very narrow. The morphology is characterized by the steep beach, and especially in the swash zone. The beach profile is usually simple, and sandbar generally are absent. There is no sandbar. For example, on this beach, it's close to Marseille, you see that, and the sediment is not sand, it's coarse sediments and pebbles. It's very common for reflective beaches. And you see that this morphology here is what we're calling cups. And these cups are a very common feature in this kind of environment. You see that the waves are breaking there is no bar, and the swash zone is in this area. And there is a lot of reflection in this area. Another example, along the coast, you see that the slope of the beach face is very important, very large, and the waves are breaking here close to the shoreline. So between these two states, dissipative and reflective, there is intermediate states. The first one is longshore bar truth systems. And in that case, waves break mainly on the sandbar located offshore. Here is the sandbar, here it is the sandbar, and the breaking process are present here on the sandbar. And after this first breaking, waves may partially reform in the deep trough located between the bar and the shoreline. And then the waves can break again close to the shoreline. The currents are mainly longshore. There is a lot of longshore currents. And this current is, of course, parallel to the shoreline. The rip currents may occur, but they're generally weak because the morphology is relatively uniform along the coast. You'll see that on these photographs here on the left. This is the shoreline position. It is along the Rhone Delta coast, and you see this line, the white line. This is a longshore bar trough system. This is the bar longshore, and this is the trough. And you see that the bar is a regular rectilinear and parallel to the shoreline. Have a look on these photographs on the right. You see that the waves are breaking there, you see, close to the shore, and there is another breaking. And actually, there is several longshore bars with no interruption, very homogeneous, two-dimensional bars. Here, the outer bar. After, this is the trough, when the wave can move, form again, and break again. And if you look carefully, you see that there is another trough, very, very small, and a break close to the swash. The rhythmic bar on beach states, in that case, waves still break on the nearshore bar, they're breaking there, but the bar is not straight. You should keep in mind that the bars are straight only on the longshore bar trough systems. Instead, it shows a rhythmic undulation. You see this rhythmic undulation, and this rhythmic undulation are present along the shore. This variation influences where and how waves break. It is connected to wave breaking. The currents become more organized than in the previous states. The undulation of the bar creates preferred pathway for moderate rip currents. Here, you may have some moderate rip currents. The morphology therefore shows a rhythmic pattern along the beach. Sometimes, depend of the point on the line you are looking for. Here, for example, it is this part. You'll see that you have a reflective domain close to the shoreline, but a dissipative domain before the breaking point. And if you are looking along this line, you'll see that the dissipative domain is more important concerning this part. Few examples. On the left, you see this very nice rhythmic organization. This is a rhythmic bar and rip states. The rip current are probably present here in that part. This is the outer bar. If you look in detail, some bars here are rhythmic again. And of course, the morphology close to the swash and on the shoreline could be like this with the presence of cups. Here you can see that. And if you look carefully, in that case, perhaps that the bar start to connect to the shoreline. So in that case, we have a different state, which is the next. The next is the case when the transverse bar connect to the shoreline. This is a more complex three-dimensional beach morphology. Waves break on the sandbar that are not longer parallel to the shoreline. Instead, the bars become oblique or transverse. In that case, you see that they are transverse bars. The currents are dominated by strong rip currents. These currents flow seaward through deeper channels between the bar and strongly influence sediment transport. The morphology shows strong variability along the shoreline, and sandbars are often connected to the beach at the horn of the beach clubs. You may have a look on these pictures. If you look this part, for example, you see that the bar is organized in the transverse and it is connected to the shoreline, always in that case and in that case. And between this connection, there is a rip channel because of strong rip currents in this kind of beach states. And the last morphology, the different, is what we're calling ridge runnel or low tide terrace. And it's often observed on beaches where tide play a more important role than previous morphology. Wave breaking change depending on the water level. At low tide, waves dissipate their energy across a shallow sandy terrace located offshore. The terrace is this part, a very horizontal part represented here. At high tide, waves break closer to the beach, and reflection process may become important. When the water level is high, is close to this part, there is more reflection process. In this morphology, currents are therefore strongly controlled by the tidal level. At low tide, circulation is usually weak and speed across the terrace. At higher tide levels, the swash motion, of course, becomes stronger. So this morphology is characterized by the relative flat sandy terrace. Some pictures on the left, you see this part, horizontal is the terrace, and we are probably at low tide, and the waves are breaking here. The water is coming in the runnel, and after probably is moving along the shore that way and return to the sea. The same in these right photographs, when this part is the terrace and there is a little runnel in this. Okay, so now you know all the morphology you can observe on the field, but these morphology are strongly related to the wave's action. So they are moving through time. You see that in the same place here. Along the shore, in that case, on the right, you see there is two longshore bars. Very nice. This is a longshore outer bar and the inner bar. And in the same case, you see that the longshore bar, the outer longshore bar, is still longshore, but a little bit different. And this one transforms into a transverse rhythmic bar. So the morphology can change through time, not exactly through time, but through the season. And the last point, I speak about the morphology and show you only one bar, but on the field, you may observe 1, 2, or 3 bars, and sometimes more. And so a combination is possible in that example. You'll see that on the offshore, the bar is longshore. This is a longshore bar proof system. But here there is undulation. So this one is more connected to rhythmic bar and beach. So keep in mind that morphology can be quite complex, and this kind of model are very useful to describe a morphology. And you need to focus on this morphology to understand how the system is working. It is the end of this session. Do not forget to read the document connected to this video. And you also will have access to a virtual tour on the Rhone Delta. And I hope that you enjoy that.